Hey everybody, this is PatrickJMT and I'm partnering with Chegg in this video to talk about continuity in calculus. So we'll give a definition of continuity at a value A. We'll talk about types of discontinuities, and we'll talk about continuity or a function being continuous from the left or continuous from the right. So continuity, intuitively, I think is relatively straightforward. If you can graph your function without ever picking up your pen or pencil, we would say, oh, it's continuous everywhere. Well, sometimes there may be breaks or, for example, a little hole in my graph. Well, at that point, we would say the function's not continuous at that point. So in this case, what I want that point to be filled in, right? I would like for it to be filled in, that hole doesn't exist, and we can just keep going. We could say, oh, it's continuous. So notice we have the limit as x approaches a of our function. Well, as x coordinates get closer and closer to a from the left or from the right, notice those values will get closer and closer to that value L. What we would like to have happen is that f of a equals L. So if f of a happened to equal L, if f of a equals L, the hole would be filled in. The hole would be filled in. We would now have this value there. And, well, the limit equals L, f of a equals L, so we can say the limit as x approaches a of f of x equals f of a, because they both equal L. And if this happens, we say f is continuous at the x value of a. And notice we talked about 2, so the limit as x approaches a of f of x, it's understood that this limit exists. And for a limit to exist, that means that the left-hand limit, the limit as x approaches a from the left of f of x, that has to equal L. And likewise, the limit as x approaches a from the right of f of x has to equal L. Remember, for a limit to exist, left-hand limits have to equal right-hand limits. So this is something you'll often have to use when you're doing these questions involving continuity. So another thing to think about. So types of discontinuities. So we just had this, the example I looked at. This is called a removable discontinuity because the idea is you could, well, remove the discontinuity just by filling in that single point. That's how I always thought about it, at least. So here we, notice in this case the limit exists. The limit exists, but the limit as x approaches a of f of x, that's not going to equal the function at a because f of a is undefined. So they don't equal. But notice the limit does exist. So the limit exists. A jump discontinuity. So here it's kind of like there's a little break in your graph. Notice here the limit as x approaches a from the left doesn't equal the limit as x approaches a from the right. Right? As we approach a from the left, I'm getting some y value up here, so that would be the limit from the left. And if I approach a from the right, I'm getting closer and closer to some y value down here. So sometimes you'll get questions where they're like, classify the discontinuity. And in this case, if I know that the limits aren't equal, I know there's a jump discontinuity. Notice that the limit as x approaches a from the left in this case, that does equal f of a, right? If you plug, so as x approaches a from the left, we're getting closer and closer to this y value, whatever it is. Well, if we plug a into our function because it's filled in, we have that this condition is satisfied. So this is known as being continuous from the left. Since my function is not filled in down here from the right side, it's not continuous from the right. And that's the notion of continuity from the left and being continuous from the left, being continuous from the right. The other type of discontinuity is an infinite discontinuity. And in my example, it doesn't always have to be this way, but in my example, as I approach a from the left of my function, well, as I approach a from the left, notice my y values get bigger, bigger, bigger. So in this case, I'm getting positive infinity. So in this case, I already know that I've got an infinite discontinuity based on that. And it could have gone to negative infinity and The same thing on the right. It could have gone to positive or negative infinity. But if you see a limit going to infinity, well, you know you've got an infinite discontinuity. So a useful theorem. So if f and g are continuous at a and c is a constant, the following are also continuous. Again, it's kind of the rules of how we can work with things. F plus g would be continuous, f minus g, c times f times g, and the quotient as long as we're not getting 0 in the denominator at that value. Another very useful important, the following functions are continuous at every number in their domain, so you can read them all. A lot of the common functions that we see are continuous, and continuity is a nice property because you just know there's no breaks or holes in your graph. So this would be an example of, I think, a typical question one could see in a calculus course, and of course there's more. Where is the following function discontinuous? We've got f of x, we've got a piecewise function here. It's 2 to the x if x is less than or equal to 1, 4 minus 2x if x is between 1 and 3, square root of x if x is greater than or equal to 3. Well, okay, I've got an exponential function. This is a polynomial function. This is a root function. And it says polynomials, do I have them all down here? Root functions. Exponential functions are continuous on their domain. So all of these functions are defined on their respective domains. So the only place there might be an issue is where they break apart. So what I need to think about is the limit as x approaches 1 of f of x. Does that equal f of a? But again, my a value is 1, so I'm going to ask myself that question. So again, there's a little break at 1. And I also have to look at the limit as x approaches 3 of f of x and think, well, does that equal f of 3? Because that's where they break off over here at 3. So I've got to answer these two questions. Well, to start off with, I look at the two limits. So first I want to figure out if the limits even exist. So I've got to look at the limit as x approaches my a value, which is 1 from the left, and I have to look at the limit as x approaches my a value of 1 from the right. Now, if we're looking at values to the left of 1, well, I'm using x values smaller than 1, which means I need to be using my exponential function. So I would get 2 to the x. Well, I can just substitute that in. I would get 2 to the first or 2, so no problem. Now, if I look at as x approaches 1 from the right, that's going to be values just a little bit bigger than 1, and that would fall into this interval, x values between 1 and 3. So then I have to use my function 4 minus 2x. And if I plug in, again, x equals 1, I would get 4 minus 2, or 2. So the limit exists. The limit equals 2. And notice if we plug 1 in, well, let's see, 1, where do we use 1? We don't use it here because it's not included. We would use it in our first function because it's x less than or equal to 1. So I would get 2 to the first or 2, which we really already evaluated. So this limit does exist. So we would say it is, yes, continuous at x equals 1. So we're in business there. Same thing for the other question. Okay, the limit is x approaches 3 of f of x. I've got to look at the limit as x approaches 3 from the left. I've got to look at the limit as x approaches 3 from the right. So if I'm taking values of 3 to the left, that's a little bit smaller. Again, that would correspond to this domain, which would correspond to this function. So I would have 4 minus 2 times x. Again, I'm just going to plug in the x value of 3 because this is a polynomial. So I would have 4 minus 2 times 3, that's what, 4 minus 6? 4 minus 6 is negative 2, okay. And then if I plug in something larger, a little bit larger than 3, well, now I'm using this domain, so I'm using this function, square root of x, but I can just plug that in and get square root of 3. And since the limit doesn't exist, it's not continuous. Continuous. Notice the limit, well, let's plug in f of 3. Notice if we plug in f of 3, again, that would correspond to this domain or this function. That would be square root of 3. So it's not continuous at x equals 3, or the a value of 3. It is continuous from, in this case, the right, because we said if we take the limit as x approaches 3 from the right, of our function, we get square root of 3, and that's what we got when we plugged 3 into our function. So it's not continuous in general, but you could say it is continuous from the right. And again, since I know that the left-hand limit is not equal to the right-hand limit, I could even classify this. I know, again, that this is going to have to be a jump discontinuity. My graph would look something like that. So, okay, this is the idea. Another common mistake, be careful, a very, very common mistake. When you're evaluating limits, be careful which function you're using. I've seen people just like plug things into every single piece of the piecewise defined function. You don't want to do that. Based on your x values, whether it's smaller than 1 or larger than 1, as in this example, or less than 3 or greater than 3, it's going to tell you which of the pieces of the piecewise defined function to use.